In the last video we discovered that the stability of simple systems is determined by the position of their poles in the complex plane. And in this video we're going to generalize such result to systems of arbitrary order. And to do so we'll apply the same procedure as in that video. We'll first find the inverse Laplace transform of the transfer function, or in other words the impulse response of the system, and then we'll check that the area under the curve is finite. So our starting point is a general transfer function g of s. Let's assume that we've already found the poles of the transfer function, which are p1 minus p1 and minus p2 minus p3 and all the rest until minus pn. And to be more general, let's assume that each one of those poles has its own multiplicity. For example, minus p1 appears k1 times, minus p2 appears k2 times, and so on and so forth. The numerator is written just as n of s because we won't use it in our calculations. As we know, the numerator doesn't affect stability. The zeros don't affect stability. So according to this, the partial fraction decomposition goes as follows. We begin with the first pole. So g of s is equal to some residue r1 1 for the first power of the first pole plus r1 2 for the same denominator squared, and then r1 3, r1 4 and all the rest until r1 k sub 1, the last residue, over s plus p1 to the k1. So all these fractions are associated to this pole. So we have to add the fractions associated to the second pole, this one here, and that is r21 over s plus p2 plus r22 over s plus p2 squared, and all the way to r2, and here the multiplicity is k2, so 2k sub 2 over s plus p2 to the k2. Now all the rest we would have to write a row for each one of the poles until we get to the final pole, and these terms would be rn1 over s plus pn plus rn2 over s plus pn squared plus all the rest of terms until rn kn over s plus pn to the kn, and these are all the terms in the expansion. So now we're ready to apply our inverse Laplace transform table. So g of t is equal to, okay, this term here leads to r11 e to the minus p1t. The second term is transformed to yield r12 times t times e to the minus p1t. Okay, this t would be divided by 2 minus 1 factorial, so I'll leave it just that way, plus all the rest of terms until r1 k1 times t to the k1 minus 1 times e to the minus p1t, and this t has to be divided by k1 minus 1 factorial. Okay, let me do quickly the second row. Here it is, r21 times c to the minus p2t and all the rest of terms. So we would continue with all the rest of terms, and we would finish with the last row, r n1 e to the minus pnt, this is for this term, plus r n2 times t, again t over 2 minus 1 factorial, which is just 1, times e to the minus pnt, plus the rest of terms until r n kn times t to the kn minus 1 over kn minus 1 factorial e to the minus pnt. This is the general expression for the impulse response. Now, if we had to draw the response according to this expression, realize that the key point is in these exponentials. If all these exponentials have a negative real part, we know that each one of those terms eventually disappears. So all of them disappear, as long as the real part in each one of these poles is negative. And if all terms disappear, then obviously the integral converges. There is some finite result. But if only one of those exponentials is positive, then we can't find the integral of g of t dt, because the terms associated to that pole will grow without bounds, and they will define a growing area that would make impossible to find this integral. So we can give the criterion graphically. If this is the complex plane, we can say if all poles are in this side of the plane, well, this is something like this. If all of them are in the left half plane, if all poles are in the left half plane, then the system is stable. And if just one of them, or maybe more, but with only one, if one of them is in the right half plane or in the imaginary axis, just one of them, although if there are more, obviously the system is also unstable. The system is unstable. One pole in the right half plane, system unstable. And this is what we have to remember. We need all the poles to be in the left half plane to have a stable system. But remember, we mentioned a peculiarity when we had poles in the imaginary axis, like for example this pair of poles, or maybe a pole in the origin. In that case, we said that the system is still unstable in the Bibo sense, but we call it marginally stable. And the reason is that if we have these simple poles, we can go here and see that, well, some of these terms in the first column will not disappear, because the exponential, the real part of the exponential would be 0, and then we would have some constant here, which is multiplied by the residue. So the output would not grow beyond bounds, but the area under the curve will be infinite. And we saw that the particular case was just one pole in the origin, and then this was the response, and this was marginally stable, and also this was the response for a complex conjugate pair. Again, this area does not converge. But if the poles are double, so we have here 2 poles and another 2 poles here, so the multiplicity of this pair of poles is more than 1, then we have this term is not 0, or it doesn't tend to 0, and also this term does not tend to 0, and here we have some t. And that's why in this case the system is not marginally stable. Even though the poles are in the imaginary axis, the system is unstable straight away. There's no nuance here. It is not marginally stable. And the same thing happens for the double integrator. If we have here 2 poles, the system is not marginally stable. It is unstable, and only unstable. Okay, I hope things are more clear now. In the following videos, we'll learn how to find out whether a system is stable or not when we don't know the position of its poles.